Okay, so I'm Dan, like I said. I live in New York City. I work at the Center for Computational Astrophysics, which is part of the Flatiron Institute, which is part of the Simons Foundation. We're not affiliated with any university or something like that. It's a privately funded center right in the center of Manhattan, and it's a pretty cool place to work and visit and all of those kinds of things. So, think about it as a place to come visit and work at. And I mostly study exoplanets. I guess sort of historically, I mostly study exoplanets. I'm on Twitter. My handle is Exoplaneteer. These days, I'm not working so much on exoplanets, but so what the heck am I doing here? Good question. But I'm having a great time, so. But I think one of the reasons why I'm here is because I spend a lot of time writing software for data analysis in astronomy and sort of learning about software and data analysis techniques that are generally useful. And when I do this, I really try to think about the implementation and the actual real live use cases of astronomical applications of that software. And so it's fun to be at a meeting like this, working in a field that I don't know very much about, to sort of see the kinds of problems that you face in your data analysis, and perhaps there are some useful things that I can contribute. And that's what we're going to try to do here. And so besides implementation, so I think a lot about like APIs and things like that and documentation and those kinds of things, and that's not going to be a big part of what we talk about today. But I also try to like learn about new methods and share them. And so that's going to be the focus of today's presentation, is sharing some things that I'm excited about. And it's a little, it'll be a wild ride, and I'll try not to wax too philosophical. There are folks on Zoom. If you don't know already, there's a super creepy robotic hand in the room. So please feel free to exercise that right, because I can't see the chat or anything. So please feel free to ask questions. And in the room, like I said, we're going to go all sorts of places. And I've either prepared 20 minutes of material or an hour and a half of material. And so please interrupt me, and we'll chat as we go. Good. So I'll start with sort of some of the punchlines that I'm hoping to get to today. So one of them is that we're doing ambitious data analysis, many people in this room are already doing very ambitious data analysis, and sort of in that context of doing these ambitious data analysis projects. What I wanted to say is that there's been a lot of discussion of machine learning today, and that's going to come up some more. And what I'm going to say today is that even if you're not doing machine learning, there are probably some useful tools, and I'll talk about that. Using those tools is sometimes easy, and it's possible that these tools that I'm going to talk about today, you can just like plug in your problem and just roll with it. And sometimes it's a complete pain in the ass. And I'll talk about some examples of that. And given all that context, it might be a pain, but it might also be worth it. So they're going to be. I'm going to try to motivate that. Learning some of the things I'm going to talk about today is worth thinking about. Good. So let's start with a little context. Every single talk so far has had Bayes' theorem written down in it and stuff like that. So I'm not going to go into too many details. I write it a little differently, but we want to collect some data, say something about physics. That's the whole story. In general, we can more easily compute in this direction. We've heard a little bit about what to do if you can't compute in that direction, and I think Kyle's going to talk some more about that after the break. But one thing that I wanted to say that's like a bit of a pet peeve is that, so there's been a lot of discussion of Bayes' theorem and sort of the posterior being the thing, being the product. And what I would say is that that's not, I don't entirely agree with that framing of the problem, and that in fact, the goal is to do integrals of this form, right? So everything that we ever want to do, with Bayes' theorem and probabilistic data analysis can be written. I didn't know how to write an integral sign in ASCII, so it doesn't have one, but an integral of this form where you have some function of your physical parameters that you're integrating weighted by the posterior. And that in fact, this is the quantity, like this is the operation that you always want to perform. And so the end product is not really the posterior, it's some expectation under the posterior. And it might sound a little pedantic, but I think it is useful to remember that that's always what you're doing. And that samples from the posterior are just a way of doing integrals and sort of generating a product, a representation of your density that can enable all sorts of different integrals that are the kinds of things that you would want. So, like I said at the beginning, this talk is going to be a talk about doing these integrals. So a few things that I wanted to point out when we're here is that this integral is often high dimensional. So the physics here is lots of different things. It includes the properties of your merging black holes, but it also includes the properties of your detector and the background noise, and there's some very high dimensional object that we want to do this integral over. And then the other one that's like somewhat unique to our fields, but not totally, is that I wonder if I can no, I can't figure out how to do that. So that the bar in the middle of our, the connection between the data and the physics, there's a lot going on there, right? So beyond being high dimensional, we're bringing in our physical model, or like numerical relativity or whatever is like enters in that bar, and that's something that all of you are very familiar with, but is one of the reasons why sort of off-the-shelf techniques don't always work for the kinds of problems that we're trying to solve in astrophysics. And in practice, a lot of the time, the way that function is encoded is in like a Fortran library that's been handed down through the generations, or I don't know if that's true for all y'all, but maybe C++ if you're lucky. Good. Okay, so all that to say, everything that you ever want to do looks like an integral like this, and I'll fight you if you don't think that's true. And so how do we do this? One option is to use Monte Carlo techniques, and there are lots of reasons why you might want to, and we've heard a lot about these kinds of things so far this week. And basically the idea is that you generate samples from this density, and then you can use those samples to do all of those integrals. And the error on that integral will scale with the number of effective samples you have, but it doesn't scale with the dimensionality of your problem. So at least in principle, this kind of method can scale to whatever dimension of physics you want to treat. Good. So to answer everything in one thing I meant to say on this slide is, so I've said one option is to do this. And I think it's important to remember that since our goal is to do integrals, this isn't the only option, right? So for example, if our physics was low dimensional, we would be much better off gridding up our space and using a quadrature, or perhaps we could even plug that integral into Mathematica and get the answer. That would be very cool. And so there are lots of cases like that where sampling is not the right approach. Alternatively, there are other methods like variational inference that some of you might have heard of that are another way of doing these kinds of integrals. And I'm not going to talk about that at all today, but a lot of the tools that I'm going to talk about also can enable you to do things like variational inference that could be very useful for the kinds of population analyses that people are thinking about doing here. Good. Sorry. It's hard doing this in a mask. You see, in my job, I don't have to teach, and so I don't have any practice with this. Good. OK, so this is the thing we have to do. We're doing integrals. And for the rest of the talk, I'm going to focus on Monte Carlo methods for doing these integrals. Good. So all you need to do is you need a good sampler. I'm going to define what good is. And for everything that I'm going to talk about today, we need some way of evaluating the likelihood function, or something that's proportional to the log posterior. Those are the pieces that we need. That's it. So the story is pretty straightforward. OK, so what is a good sampler? A good sampler is a sampler that generates independent samples from that density without being too expensive. So a small number of model evaluations per independent sample. That's the thing that matters. And that's sort of an important thing to remember. Various people have brought up that the samples from a typical MCMC will be correlated. And so it's important to remember that and sort of think about that. And in fact, one thing to remember is that the number of effective samples that you get actually depends on the function f that you're integrating. So for different targets, you might have to run your sample longer or not as long. But in general, this thing, besides depending on f, it also depends on the dimensionality of your problem and also the geometry of your problem. So if you have like really super multimodal or crazy covariances and things like that, sort of how good a particular sampler is can vary. OK, so then part two, which I'm not going to talk about quite as much today, is our fast probability calculations. We want our models to be interpretable. And there are tools that we've heard about and are going to hear more about for sort of speeding up while retaining some of that interpretability. But that's sort of a fundamental part of what we care about. And then this kind of calculation will generally scale with the size of our data and the kinds of simplifying assumptions that we're willing to make, right? And that's also familiar to lots of people here. And so here's a list of the kinds of things that we care about when doing inference in astrophysics. We want to get the right answer. We want to be able to do it with large data sets. And we want to use our sort of physically motivated or physical models. And hopefully we'll get our result in a finite amount of time. That would be great too. So what do we do? Well, one thing that we might do is we might Google MCMC for astronomy, and we might find this documentation page for a piece of software that I wrote called MC. And after the talk earlier today, you might also find Dynasty, and then you might implement your model inside of one of those frameworks. I know that there are other packages that people use here, but these are some examples. And I won't talk smack about dynasty, but I can, as the author of MC, say that MC is not a very good sampler. All right? There are lots of reasons why it can still be useful to use. It has a nice interface. It's sort of, it's well suited to some of the low dimensional problems that we might want to do. It interfaces nicely with your Fortran code, but in fact, it's pretty shite. And here's a graph explaining why. And so this is super scientific. So here I'm plotting the dimensionality of the problem and how long you have to run your supercomputer for. And if I plot a typical MC type of run on here, it looks something like that, which is to say that if you have more than a couple of parameters, things start to get pretty ugly. And that's also true for things like dynasty, like Josh was talking about earlier today. The slope won't be the same necessarily, but it also suffers from these kinds of problems. Now, we might prefer things to be a little bit more like this. If I'm fitting a much higher dimensional model, I'm willing to pay a little bit more cost, but I don't want to have to wait forever. And so, this is the kind of this is our goal, to get something that doesn't scale so badly with the number of dimensions. Good. So I've asserted that with things like MC and dynasty and some of the other tools that we're familiar with, we can get the right answer if we're willing to wait long enough. We can work on huge data sets because it's up to the user to evaluate their model, and there's a huge history of quickly evaluating astrophysical models in all of the fields that we work in. Those samplers play nice with the handed down Fortran code, but for the kinds of real life problems that we want to do, it might just take way too long to actually solve them. And so what do we do? Well, it's a solved problem, sort of. And the answer is, at least in some cases, gradients. Good. Well, there are other answers. So let me step back for a second. So I mentioned earlier that depending on your problem, you might be able to solve the integrals directly that you want to do. So for example, if you have a very high dimensional linear model, then you can compute any kinds of integrals that you want, even if you have millions of parameters. And so in those cases, you don't need to use any of the kinds of things that I'm talking about. Similarly, your problem might have structure in it. There might be some parameters that are independent from each other, and you can do clever things like break up your problem. And in fact, we've talked this week a lot about sort of parameter estimation and population inference as sort of separate steps. And in many ways, that's like a clever way of exploiting the structure of your problem. You're assuming that you can independently analyze each of your events and then combine that information into some population level inference. And I think that there were already some comments about, maybe we should just do all of that together, right? And in many ways, that's sort of the right answer. If we want, if you wanted to directly figure out what information is in the raw data, what that can say about the population, then you might want to do all of that inference together. But instead, we don't know how to do that, and so you break it up into this two-level kind of process, and that's super common. But another thing that you can use, so another type of, if you can't exploit those kinds of structures, something that you can use is gradients. And when I say gradients, what I mean is the derivative of your model with respect to the physical parameters. So you're using some higher order information about the shape of the surface that you're trying to sample from, and that can give you more information to come up with better proposals, and in fact, this can help you scale to much higher dimensional problems in finite time. This might seem like a scary thing. I mean, it doesn't look scary on this slide, but I think you can start thinking about how you would implement this in your code, and it sounds not very fun, but we'll get to that in a second. But I wanted to sort of motivate, in not too much detail, the idea and why these derivatives help. And so this is going to be very schematic. So don't quote me too aggressively. But so the kinds of things, the thing that we're trying to do is we have some log probability that looks something like this, and we're trying to generate samples from it so that we can do integrals. And what you could do, you can't stop me, is you could multiply that by -1, and then this suddenly starts to look something like a potential energy. And then, for reasons, you might imagine that your MCMC sampler is some particle living in this potential, sort of moving around in this potential. And in that case, your MCMC walker now has a kinetic energy as well. And so the idea is that you give it a little kick, and then it's going to zoom around in your potential. And the way that this works in practice is that now we have twice as many parameters. So here I've labeled our coordinate, like the physics dimension, as q, and then we have some momentum for our particle. So that's the same dimension as our parameter space. And now we have twice as many parameters. And I'm asserting that, in fact, you can get better MCMC samples from this procedure, which doesn't seem obvious, but I can give you a very quick reason why. So what you can imagine here is that now this kinetic energy is the negative log probability for the new set of parameters P, the conjugate momenta. And now that we have a setup like this, we have all of, we know how to integrate a dynamical system like this. So we can, starting from some position and momentum, we can run a leapfrog integrator or something like that for some number of steps, and we'll get to some new part of parameter space. It turns out that if you do that and you conserve energy, then what you get is you get an MCMC proposal, a Metropolis-Hastings proposal, with an acceptance probability of 1, because the thing that you're accepting on is the difference in energy between your two states. And so what that means is that if you work in this higher dimensional space and integrate your system, treating it as a dynamical system like this, you can get MCMC proposals that will be accepted every time. So you're never throwing away a sample. Sorry. Any questions right now? Good. Okay, so this is a little crazy, and I'm not going to give you any more details, really, except to say that there's sort of like a class of problems that are based on this basic idea, doubling the number of dimensions, doing something clever to integrate your system, and that you get really good acceptance probabilities. Yep.
So I imagine that every now and then you need to give a random kick again to the ball, because otherwise you cannot explore higher up than where you are.
Mm-hmm. Absolutely. So in fact, the way that it works is a sort of Gibbs type of thing, where you would do a proposal in the momentum, give it a kick, And the way that you do that is you would actually directly sample from the negative exponential of the kinetic energy. So in fact, people would normally like assert that the kinetic energy is Gaussian. And then you would do a proposal using the Hamiltonian integrator. So that's the way that it works in practice, to explore between the levels. That's a good point. Any other questions? Good. Okay. Clear as mud. Okay, so we're done. Oh yeah. Gradients. What do gradients have to do with this? You may remember, I didn't really remember before I started working on this from my high school dynamics class, that in order to integrate these systems, you need the derivatives of your kinetic energy and your potential energy. And in this case, the potential energy is our negative log probability, so that means that we need those derivatives. And so that's where the gradients come in. So we need them to do these kinds of integrals. And so we're done. We can do that. Maybe you might be able to, Google how to do these things, and you'll see a set of logos that look something like this, and you might just be able to do it. But we're going to talk about specific tools in a few minutes. But I think you'll find that in practice, this can be a little tricky, sort of just like figuring out how to translate the kinds of things that you want to do into one of these frameworks. And the reason is this. So I've asserted that we can get the right answer using some crazy idea like this Hamiltonian based sampling. We can scale this to large data sets for reasons I'll talk about soon. And I'm also just asserting that these things scale well with the number of dimensions. So people have used these kinds of models for million-dimensional problems. But the problem is this physics-based model. So we want to plug in our numerical relativity code into that model. And so we need to be able to take its derivatives. We need to be able to compute this object, which I said might look a little scary. And the reason why it's scary is because there's a lot going on in that bar that we don't necessarily want to have to re-implement. And so in the real world, the way that this is handled is with a set of ideas called automatic differentiation. And the basic idea, and some other names for this are backpropagation. So if you've worked in deep learning, that'll be very familiar. It's all sort of, they live within the same world. And the basic idea with this is that your model, like that function to evaluate the potential energy, is just code, right? You've written down some set of operations that evaluate it. So you can take your code line by line, go through it, and just apply the chain rule over and over and over again to each line of your code. And what that does is it gives you some function for evaluating the derivative of your model at some point in parameter space. That's a little insane, right? Interestingly, it's not quite as crazy as it sounds. And part of the reason for that is that there's been, since this set of concepts is the entire backbone behind things like deep learning, there's been a huge investment in making these kinds of operations very efficient and sort of have user-friendly interfaces and things like that. So in fact, this auto-diff idea kind of just works in lots of cases that you might not even expect it to work. So a few things I wanted to say about about this is it's important to realize, so automatic differentiation is not the same thing as numerical differentiation. It's not like taking a tiny step in each of your parameters and computing what the derivative is based on that. Similarly, it's not symbolic differentiation. So it's not like figuring out what the expression is for the derivative at some point in parameter space. Instead, what it's doing is it's piecing together a function that can evaluate your derivative at some point in parameter space, which is subtly different. And so it can handle things like conditionals and for loops and those kinds of things. And so that's pretty cool. And there are implementations of this in all sorts of languages, and I'll talk about all of that in just a few minutes, if I don't lose my voice. So that was all a good story, but then here's an example from my work, which is like the most trivial example of why this is hard. So here's an equation that is probably familiar. And this equation is Kepler's equation. And in all of my work, I want to solve this over and over and over again. And I want to solve for capital E given capital M and little e. And the idea here is that there's sort of a long history of, there's like hundreds of years of algorithm development that has gone into solving this equation right here. And so I don't want to have to re-implement that inside of one of these model building frameworks. And similarly, a lot of those methods are iterative, and I won't necessarily want to apply autodiff to an iterative method. So you don't necessarily want to apply the chain rule through the iterations of your Newton solver at each step. And so I think that in your cases, the kinds of models that you're looking at have similar properties. You're numerically solving something, and you want to be able to differentiate it, to put it into a modeling framework, like the kinds of things that I'm talking about here. But you don't want to have to rewrite it inside of their framework. Unfortunately, I don't have an answer to that, but there are some tricks that can make it more feasible. And so what I've spent a lot of time thinking about is how to, I have some solver for this equation written in C or C++ or Fortran or whatever, and I've figured out how to expose that solver to something like TensorFlow or some of these other frameworks. So you can call into your solver and just expose that part of the model. You need to expose the custom code, and then you also need to know how to differentiate it, which is tricky. But we can talk about that more specifically offline, because I'm going to run out of time. So all of the recommendations that I'm going to give in just a second have support for doing this kind of thing. So what you want to do is you want to isolate the part of your model that's like physical and that isn't just sort of a set of simple operations, and expose that through this kind of interface. Good. Okay, so I've sort of talked a lot about the theory, the kinds of things that you would want to do. So how would you go out and do this in your work today? And so I have a set of recommendations, and I'm going to try to give you some thoughts about all of these things. But I should say that I mostly work in Python these days. That doesn't mean that Python's the best place to do these things, but that's what I do, and I think probably lots of people here also use Python. This changes. The last time I gave a talk like this, my recommendations were different, and it wasn't even that long ago. And so this is a very fast-moving field, and there's lots of exciting new open source development happening all the time. And similarly, there's, as a result, there's lots of different tools being developed, new tools, and so I'm not going to list everything that you could use. So given those caveats, here's sort of the state of the field for open source tools for doing these kinds of things. And you might recognize some of these logos, especially for people who have done a lot of deep learning, is that you might think, TensorFlow, PyTorch, these are tools for building neural networks. And that's true at some level, but what I would argue is that they're also tools for building differentiable probabilistic models for physics-based inference. And the catch is that you have to figure out how to expose some of your C code to them, but that's true kind of across the board here. So that's the middle layer there, where those are sort of deep learning tools that have GPU support. Things like that are sort of very well established, and depending on the structure of your problem, could be really good. On the top line, there are sort of the tools that are specifically for doing probabilistic inference. So PyMC3, or I guess maybe they've renamed it as just PyMC now. And then Stan are sort of two of the top tools for doing MCMC using Hamiltonian-based samplers. And of the two, I mostly use PyMC because it sort of has a nicer Pythonic interface, and it's very easy to extend and add custom C code to, whereas Stan is a lot harder to do that with, but also gets the most development, and sort of new algorithms are implemented first in Stan. And then the one that I'm most excited about is on the bottom here, JAX. And there's sort of an ecosystem of tools that are built around JAX for doing gradient-based inference. And so I think it's sort of the youngest of all of these and the least mature, but it has support for GPU calculations and all of the other things that we want, and it's very easy to extend. So I'm really excited about it. So my current recommendation, if you're just starting this today, is to try out JAX and NumPyro, which is, I think, sort of the best inference framework built on top of JAX. And the thing that's cool about JAX is that it exposes a NumPy interface. So if you're already writing code in NumPy, you can write it in JAX NumPy, and almost everything is supported. And then your code will then be differentiable, and you can just run it on GPUs and TPUs and these kinds of things, for free. I don't want to be too much of a business person. There are limitations, and I'm happy to talk about all of those things. But it is super cool, and it works really well. So that's what I would say is sort of the best recommendation. But like I said, I have all of those caveats. JAX is a Google product, and Google has a long history of cutting us loose. So, be that as it may. So I wanted to talk very quickly about a sort of set of projects that I've done in this space, just to give you a sense of the kinds of things that exist and some of the benefits of the tools that I'm talking about. So. I've been building this package called Exoplanet. I've been working on it for the past couple of years. Like I said, this is a moving target. So Exoplanet is actually built on top of PyMC, not JAX. But I've done lots of work sort of starting to transition. And the idea with Exoplanet is to provide a set of exoplanet-specific functions that you need to analyze exoplanet data using PyMC tools. And so it has a Kepler solver and some other things like that. But this is actually ballooned a lot. And in fact, it should have been called time series or something like that. And so exoplanet kind of scares people off. But actually, I think that there are probably some things that would be useful for the kinds of projects that people here are thinking about. And so In particular, there are lots of introductory tutorials and stuff along the side that are not really exoplanet specific that might be a good resource if you want to get started thinking about these kinds of things, including sort of tutorials about auto-diff and things like that. And then more specifically, there's a tool in there called Solarite, which is a fast, scalable Gaussian process code that has support for PyMC and JAX and all of these other things, with the engine written in C++ and then exposed to all of those frameworks through a common interface. And I'm basically out of time, so I'm not going to talk about this in too much detail. But I think, first of all, I think there are ways that this model could be immediately applicable to gravitational wave data analysis. And there's sort of a set of generalizations that we've been working on that I think would make it especially interesting. So things like, there's been a lot of discussion of sort of requiring stationarity in your noise processes in order to switch to the between the Fourier domain and the time domain. This kind of code, in fact, there's some non-stationarity that you can incorporate into it to model your time domain data with a Fourier domain model. And so I'd love to chat about those kinds of things. Similarly, we've recently extended to, so originally it was designed for 1D time series. We've recently extended it to multivariate time series, and they don't even have to be simultaneous. So if you have, say, multiple detectors that you want to look at the shared correlation time correlation structure, there might be sort of a set of tools here that I'd really love to talk about. Okay, so I had a few slides about this. Oh yeah, the big thing is that it scales linearly with the number of data points, which is very rad, because normally it doesn't. It's also super fast, scary C++ code. I had way too many slides. Look at me. And so this is the documentation page for that. But I think a lot of the gravitational wave applications, in fact, are sort of research projects. So I'd be really excited to talk about potential applications there. And the last thing I wanted to show about this was I've recently, I don't know if you can see that up there, but I've recently started re-implementing this just in JAX rather than writing C++ code as the engine. And I actually get performance that's basically as good as the handcrafted C++ code. So to be more of a salesman, this function right here is the same as this horrible C++ function, so it's very cool. Okay, so I wanted to wrap up by talking about giving a bit of a summary, and then talk about very quickly about some of the issues that you might face when trying to use some of these tools. So I've asserted that there are ways to check all of these boxes. And of course, the check marks come with all sorts of caveats. And one of those caveats is this issue with open source projects in general, which is that a lot of the time the documentation and tutorials are not super awesome. And in particular, if you're coming in, a lot of them are written for like stats practitioners rather than astronomers. And so the language might not be very familiar or might not be very useful. And so like the PyMC docs are just horrible. And so I've been working on trying to write documentation in the Exoplanet code and stuff like that to try to ease this process. Reparameterization is really important. I know that's something that people here think about a lot already. In fact, these gradient-based methods can be very sensitive to nonlinear degeneracies in your problem. And so it's very sensitive to like multimodality and stuff like that. So those set of ideas are super useful for thinking about when applying this, and you'll find that a lot of the time it takes some hand-holding. Once you hand-hold it through the process, it's ridiculously fast, but it can take some work. And then the last thing is that it remains hard to interface with legacy code. There's lots of work to do with that. Okay, so the big projects that we're trying to do in astrophysics, and here, I think it's worth exploring some of these tools that exist for modern methods. And it's possible that actually for some people in this room, it'll just work. Like you can maybe just turn on one of these tools and suddenly it'll speed up everything that you've been doing. And that's cool. And I'm very excited to play around with some of those problems. But that might not always be true. And so I want you to experiment with it, report back to me, report back to the community, and build gravitational wave specific tools that are differentiable and all of that kind of stuff, and let me know what you find. And this is where you find me on the internet. Yeah, that's all. Thank you so much.